Hello and welcome to the last video on the t-test and the t-distribution. We've had so far the single sample t-test, where we have just a single sample, as it says, and we are testing to see if the mean changed higher or lower, whatever. The only difference between that and the normal distribution with z-scores is that we have to, in some cases, estimate the variance where we didn't have it. Then we looked at dependent means t-test, where I'm testing like the same group of people twice, before or and after a treatment. And in that case, we are looking for the different scores and then look at the distribution of that, because the same person had a score before and after. We can just look at the change, the difference, instead of two sets of scores. However, that might not always be the case. We might have two separate groups of people, like this first example. So we are comparing the performance of participants tested in a quiet area versus a noisy area. Not the same people, two different groups of people. So the quiet condition has 5 people, and their task performance scores here. Then we have the noisy condition and 4 people, and their scores over here. These are different people, so there's no option to start by taking differences. It's not the same people. So we do assume in the background, and at the early level we don't obsess over it, but we do assume that the variances between these two populations are the same. The question is, we don't know what it is, and we want to sort of pool all this information together to get the best estimate for the variances. But before we get to that, let's just set this up. Let me move down a little bit like so, and just be aware of what the hypothesis statements are. So we're testing quiet conditions versus noisy conditions and seeing if quiet conditions improve the mean performance score. Our research hypothesis is sort of in line with what we're hoping, that there is an improvement. Null hypothesis, no improvement. Okay. So for our characteristic distribution, we have to estimate the population. And I'll start by maybe zooming in a touch here. Let's zoom in a little bit. I know some of it's going to be off screen, but we're focusing on part 2 here. We have to somehow, and we'll see soon enough, estimate and calculate the population variance. And we'll call that the pooled variance. So we'll see how we get this 3.43 in a second. Then our comparison distribution will again look at the distribution of the difference between these two samples. Or rather the distribution between these two populations, rather. Let's have a look at how the sample is, each sample can be pooled together to estimate the variance as accurately as possible. So for the quiet one, we have 5, our degrees of freedom is 4, one less. We get a sample mean here, and we get our sum of the squares, our variance for this group, 2.5. Put a line under that. And for the noisy group, we get, I guess, the lines over here rather. Boom, boom. Mean 1, this is group 1. Variance 1. Degrees of freedom 1. And then we do the same. The mean scores for group 2. Variance for group 2. Degrees of freedom for group 2. 3 because there are only 4 in the sample. Now we want to pool these together. First of all, we are going to take essentially a weighted average according to the degrees of freedom, averaging these two variances, but the one that comes from a bigger sample, higher degrees of freedom, gets a bigger weight in this weighted average. And that's how we get our 3.43. The total degrees of freedom, adding up to 2 degrees of freedom for each sample group, 7. And then the weighted average by way of degrees of freedom. The first variance gets a weight of 4/7, and the second variance gets a weight of 3/7, contributing a little less because there were fewer people. So that'll be our pooled variance, which is our estimate for the population variance. Then everything is done separately for the groups until the very end of the when we get the comparison distribution. I'm doing everything for the groups separately because the quiet condition scores have their own distribution in a sense, and the noisy condition scores have their own distribution. So they each get their distribution of means. The pooled variance over the sample size, the pooled variance over the sample size. So now I go back to, I pooled the variance, and now I go back to each of the samples to get their own distribution of means variance. Now the variance, what we're going to look at is ultimately the difference between these, but we couldn't get different scores in the beginning. We have to investigate the groups completely on their own and then merge them into a distribution of differences of means, differences between means. The variance for that distribution is the sum of these two variances for the distribution of means for each group. Because they're not the same, because their sample size could be different. So in that case, when I sort of add or subtract the two groups, the variance is the sum of the variance. Sort of the worst case. Fluctuations in one can add up to fluctuations in the other one. And then the standard deviation is just going to be the square root of that. Let's go back here to our list. I know it's a lot in the beginning, but it gets better as we go. So before we look at cutoffs or anything, we have to calculate our pooled variance, then go to each group separately again and look at our comparison distribution, which will assume there's no difference, no change. So sample, we'll have a mean of 0, and this should really be a mu, whatever. Standard deviation of 1.24. It'll be a t-distribution with total degrees of freedom. Now, I'm not able to draw very well with my mouse. However, we've seen it before. The idea is similar. Before we get to a diagram, let's just finish this. So let's choose 5% alpha. It'll be one-tailed because we're only looking for an improvement. The needed t-score, the t cutoff, Our degree of freedom is 7, 5% alpha. Let's go check. Whoops, that's a table here. One-tailed, 5%, 7, 1.895, 1.895. So these variance, before I forget, formulas are, oopsie, I pressed too many things at once. It's coming. There we go. Are in the formula sheet. We have the pooled variance over here. We have the back to the individual groups, their distribution of means, and then the variance of the distribution of differences between the means is the sum of the two variances. We then will look at, don't worry about this last one, that's for another topic. We then calculate our t-score as the difference between the two means over the standard deviation of this difference distribution. So we get our cutoff according to our alpha and one-tailed or two-tailed. We then calculate our t-score as 3.23, compare it to the cutoff. Well, it's way further than the cutoff, more extreme, therefore we reject the null hypothesis in favor of the research hypothesis. People tested under quiet conditions perform better, the evidence suggests, than those tested under noisy conditions. So once we go through this a few times, it does get better. Let's visualize what's happening here. We have our individual populations, quiet and noisy. Or is it the other way around? Doesn't matter. Just to visualize it, doesn't matter. We then go to the distribution of means for the two groups. Because their sample size is different, the distribution of means, distributions of means could be different. And in order to get that as accurately as possible, we pool the variance first and then go back to the groups separately. Then our comparison distribution is the distribution of differences between the mean, which is a t-distribution again. It's not the same as the dependent means t-distribution. So look at both and try and see the difference. In the dependent means, we had the same person taking two scores, and we could right away just focus on the difference between scores. So we had the distribution of difference scores. Here we're calculating the groups separately, and then each one has their distribution. If I merge them by way of a difference, then I get my comparison distribution. Okay, so there is a difference, a significant difference between these two that I want to get used to. It just takes some time. Now I think I clicked on the next one. Okay, so let's not show too much. Let's look at another example. Now keep in mind, a lot of these calculations, I just show the calculations. We'll have follow-up videos where we do the calculations in detail. This isn't supposed to give us all the detail at once because that's a little overwhelming. Let's just get an idea for this by way of another example. So we're trying to investigate a skills training program, and we're trying to see if that program makes a difference. So we have people that couldn't hold a job, didn't do the program, ordinary skills job program versus our special skills program. So population 2, just normal stuff. Population 1 underwent our special program. We want to see if there is a difference between the two. Or the null hypothesis says no difference, no difference. But of course, these are independent groups because once a person does a job skills program, they can't do another one. You can't be sure where the benefit came from. So they can kind of only do one of these programs. So they're definitely independent. So let's have a look at the detail. I know there's a lot of detail. Deep cleansing breaths, and we will be okay. It might cut off here, but I think we're okay. I can't really check my end results screen, so I'm hoping. Squeeze it to the left as far as we can. So it's a t-test for independent means. We have our control group, just ordinary program. Then we have the group that received the special program, the experimental group, if you will. There were, how many of them here? 6 of them in the experimental group and 8 of them in the control group. We got now this was measured as in some scoring scale, we don't know. Then we calculate deviation from the mean in order to get to the variance for this, dividing of course by sample size -1. The variance there is the estimate of the population variance from this group only. So variance 1. Then we did the same thing for the second group, the control group, and got their variance as well. There's not much more to do with the means until the very end, so it's not much to worry about right now. The degrees of freedom, of course, 1 less than the 2 sample sizes, respectively. So the total degrees of freedom will be 5 plus 7 for 12, and we'll eventually need that for the table lookup as well for our t-distribution. So now we're pooling the variances together, but they have different sample sizes potentially. So it's a weighted average of the 2 variances, and we get 4.16. Then we go back to the individual groups and get their variances for the distribution of means for each one, number 1 and number 2. Then lastly, well, almost lastly, we merge these 2 together for our comparison distribution of the differences between means, where we just add them up. And of course, for this formula over here, we need the standard deviation of the difference. So we take the square root. Then I think this is also in the list here. So we get our t-distribution, and we get these 2 numbers. Of course, under the null hypothesis, mean is 0. And that was our standard deviation. T-distribution, degrees of freedom 12, like we saw. Then let's choose an alpha of 5%. Two-tailed, because we're checking for a difference or not. Degrees of freedom, let's see where this comes from. Two-tailed test, 5% alpha, degrees of freedom is 12. Two-tailed test, 5% alpha, degrees of freedom 12, 2.179. Oops, laptop froze. 2.179, beautiful. I think I'm just moving too much for the laptop. Slowly it's getting there. So then we calculate, that's the t cutoff line on both sides. We then calculate what is our observed t-score for the differences between the means, between our sample means, one was 6, one was 3, and our standard deviation of the difference between means distribution. And we get 2.73. It's not much more, but it is more. And we can say the score is more extreme than the cutoff. Therefore, we reject the null hypothesis in favor of the research hypothesis. The new special job skills program. I want to say more effective is different than the ordinary job skills program. If you start with a two-tailed test, this is all it is saying. This is all it is saying. Be careful here. All we say is the evidence suggests that it is different. If you want to say the evidence suggests that it is better, you have to go back and do a one-tailed test, right? So we saw it again. This is a little small because if I zoom in, it's a little big. Maybe not. Maybe not. This is just an example to visualize. This comes from a different example. It's the only nice diagram I had, but that's okay. You had two populations. You calculate their own distributions of means using a pooled variance because that's the best variance estimate we can get. Then you go to your comparison distribution, which is the distribution of differences between means. It has its own standard deviation and mean t-distribution. Now, under the null hypothesis, of course, it's always your comparison distribution is always under the null hypothesis. So therefore, the mean there is 0. The issue is really around the difference. Now, that number is not going to make sense. This comes from a different example. And then you use your samples in terms of sample means to get your observed t-score and compare it to the cutoff, just like always. So I have to always ask myself, what kind of situation am I in? I'm trying to wait for the next page. We're almost there. This is just a summary that you can pause and read through that, see if it makes sense. It's a little silly for me to read through everything again. We did it in 2 examples, but we definitely want to be aware of this variance. This is the new, tricky, more detailed calculation step. So you want to always think, well, what situation am I in? If we look back from the start of where we were, just a brief summary. I can have one score, one single sample, or a sample consisting of one thing. I might know the population, let's say normal, and I know everything about it, mean, variance, normal shape. Then the population distribution I use directly. Or if I have a sample with more than one score, I'm looking at the sample mean. If I know my population, then I'll know the mean and the variance, but it's going to be the comparison distribution is the distribution of means, still normal, because I know everything about the population. Or I don't know the variance. Still a single sample. I have to estimate the variance. Then I cross over to a t-distribution. Still the comparison distribution is the distribution of means, but it's now t-distribution. Because this estimate needs a little grace in the tail, a little safety. Then the alternative is when I have 2 groups, but really 2 versions of the same group, like people taking a test twice. I then go right away to differences, still have to estimate the variance. The mean is now 0 under the null hypothesis because I'm trying to compare some sort of difference. T-distribution comparison distribution is the distribution of means of difference scores. I start with difference scores from the very beginning, and then the distribution is much simpler from that. Whereas if I have independent groups, then I don't have the luxury of doing different scores from the very beginning. It doesn't make sense. I have to analyze the groups and look at them individually, merge them for a pooled variance that I can use to get an estimate of the population variance, and then on the way to getting an estimate of the variance for this comparison distribution, which is going to be the distribution of the differences between means. These two are not the same. So spend some time and think about how these two are different and the same. The same in the sense that I don't know the population variances and I have to estimate them, and that I'm comparing means in some way, but dependent versus independent is handled quite differently. So be aware of the single sample t-test, the dependent means t-test, the independent means t-test before you move on to the next topic. That's it for now. Until next time.